Indian scientists have dished out a lesson in radio telescope construction. They have built a unique facility with which they cup an ear to some of astronomers' most intriguing questions. The Giant Metrewave Radio Telescope, known as the GMRT, gives astrophysicists from around the world a front row seat to a symphony of stars. Mankind has been stargazing for millennia, yet for most of that time, astronomers were frustrated by the light of the Milky Way, which obscured their view of a large slice of the universe. With the discovery that radio waves gained from space, we finally had a way to cut through the glare. The veil was about to lift from a host of heavenly phenomena. Professor Govind Swarup of the National Center for Radio Astrophysics has been listening to the skies for most of his life. His dream, a major radio astronomy center, built in India by Indians. This is the realization of that dream. One of the biggest radio telescope facilities on Earth. A facility with the power to reach objects and phenomena incredibly distant.
It sees the collapsing stars, it sees exploding galaxies, it sees what is there before stars and galaxies. And so it's so fascinating. The world of radio astronomy is indeed so fascinating.
The GMRT north of the city of Pune was designed to examine the long so-called meter wavelengths. This meter region of the radio spectrum had been largely ignored because of interference from radio signals generated by humans. But here, there's no problem, making this remote location ideal for listening to the universe. The facility consists of 30 steerable dishes distributed over an area of 25 square kilometers. Each dish is 45 meters across. The configuration of the dishes contributes to a powerful process called aperture synthesis. With it, scientists produce radio images with incredible resolution. Results equal to what could be achieved with a single dish 25 kilometers in diameter. What makes the site even more remarkable is the way in which construction costs were kept low. The dishes were built using a concept the Indians call SMART, which stands for stretch mesh attached to rope trusses. It's cheap, light, and because the mesh is permeable, the dishes are less likely to move in the wind. Dish stability is critical when focusing on objects so far away. The data from the dishes is collected, processed, and amplified. In effect, this cleanses and boosts the celestial signals, which then are interpreted as images. GMRT is a huge technical achievement, conceived and engineered by Indians. It's filling an important gap in our knowledge of the radio spectrum. A first-class facility for astrophysics research, GMRT is also a beacon of encouragement to India's young. Its best and brightest who might have a mind to listen to the stars.
"80 kilometers from Pune stands one of mankind's great endeavors in its pursuit into knowledge of the heavens. This is the Giant Metrewave Radio Telescope being constructed by the National Center for Radio Astrophysics near Kodad. GMRT has been designed to investigate a variety of outstanding astrophysical problems in modern astronomy and cosmology. It is one of the most challenging projects in basic sciences undertaken by Indian scientists and engineers. The Giant Metrewave Radio Telescope is an array of 30 fully steerable parabolic antennas. Out of these, 12 dishes are located in a random fashion within a central area of about 1 square kilometer. The rest of the 18 dishes are spread out along the 3 arms of a Y-shaped array. Each arm is approximately 14 kilometers in length. These antennas are spread over an area with an overall reach of 25 kilometers. Thus, the array will image the sky with a resolution equivalent to that of a single dish of 25 kilometer diameter. The operating frequency range of GMRT will be 38 MHz to 1430 MHz. The fabrication of the 30 antennas has been carried out mostly at the GMRT site by using mass production methods. 480 parabolic frames and 120 quadruped legs are needed for the 30 dishes. The skeleton of the dish is made of steel tubes and there are 16 radial parabolic frames of triangular truss work. The top tube of each section of the parabolic frame is bent to desired curvature on a tube bending machine. The shape of the bent tube is checked on a jig embedded on a concrete platform. It is then mounted on vertical supports of the jig. The 2 bottom tubes and cross tubes of proper length are assembled to make a triangular frame. The ends of the tubes are suitably shaped so as to match the curvature of the tubular surface where they are to be welded. Each parabolic frame is 17 meters long. After checking the alignment with the theodolite mounted at one end, each weld is tested using radiography. The azimuthal bearing assembly is fabricated by welding 7 sections of steel plates to form a ring. This ring is then welded to a steel cylinder and strengthened with fins. A large vertical lathe was locally fabricated for machining jobs as big as that required for a 7-meter wide central box of the yoke, weighing 14 tons. The part of the bottom plate of the central box, which sits on the azimuthal bearing, 3.8 meter in diameter, has to be machined to an accuracy of 50 microns. The 3.6 meter diameter azimuthal bearing assembly is then mounted on a concrete tower, which is 15 meters high. The yoke of the antenna is made of 3 boxes, 1 central box and 2 side boxes. Steel plates are welded together to make the yoke. The core of the dish is the hub to which the parabolic frames are attached. The fabrication of the hub requires complicated jigs. The pipes are welded on steel spheres. The hub of the dish is 12 meters in diameter. Once it is ready, it is put around the concrete tower. First, the central box of the yoke is placed on the concrete tower. Then, the parabolic frames are attached to the hub. The two side boxes are then welded to the central box at the top of the tower. The novel method has been devised for fabrication of these low-cost antennas. The entire dish of 45 meters, except the central 12-meter portion, is assembled and completed around a concrete tower, and then it is lifted. The hub of the parabolic dish is supported on the cradle, which is in the shape of an inverted pyramid of a 12-meter base and a 5.5-meter height. Like the hub, the fabrication of the cradle also requires complicated jigs. The elevation shafts are welded at the ends of the square base of the cradle. Then the cradle is lifted and mounted on the elevation bearing on the top of the yoke. The parabolic frames are aligned radially, and the elevation is checked by using a theodolite, peering through strategically positioned slots in the wall of the concrete tower. The design of GMRT antennas exploits the climate conditions prevalent in this part of India, where it never snows. By using a wire mesh instead of a solid surface, it has become possible to reduce weight and wind loading. In order to take care of the fabrication errors of the parabolic frames, adjustable studs are welded on the parabolic frames every 1.2 meters apart. The height of these studs can be changed by an adjustable stud. The reflecting surface is made by stretching a fine wire mesh of stainless steel wires 0.55 millimeters in diameter, which is attached to these studs. The wire mesh has a square grid with size 10 square millimeters in the inner one-third area of the antenna. The grid in the middle one-third area is 15 square millimeters and it is 20 square millimeters in the outer one-third area of the antenna. The wire mesh acts as a near-solid reflector for radio waves of long wavelengths. The wind resistance of the GMRT dish is about 20% of that of a dish with solid surface. The unique feature of the GMRT dishes is the use of tensioned rope trusses for creating curvature in the circumferential direction. These are made up of stainless steel ropes 4 millimeters in diameter. The parabolic surface is approximated by about 900 plane facets stretched between these rope trusses. This design, developed for GMRT, has been appropriately termed the SMART concept. SMART stands for stretched mesh attached to rope trusses. The shape of the dish is controlled by tensioning ropes using turnbuckles. The surface accuracy is then determined by measuring the angles of plastic beads attached to the stainless steel wire mesh at about 6,000 locations on each dish using a theodolite. At this stage, quadrupeds with a turret box and lightning arresters are mounted on the rim of the dish. The turret box is rotated by a gear system. The completed dish is then lifted and hoisted slowly using 4 manually operated winches. Four teams of 6 workers each synchronize the lifting operation. The monitoring of the lifting operation is done by attaching the 4 ropes to the hub. The synchronization of all the 4 winches is achieved by noting the movement of the rope. It takes about 4 hours to lift the dish. It is then attached to the cradle. The last few pieces are then welded and the inner surface is covered with wire mesh. A pin sector gear is attached along the other diameter of the square base of the cradle. 2 elevation motors are mounted on the top of the central base of the yoke and engaged in a pin sector. A plunger-type stow lock has been provided for parking the dish in a safe condition in case of high winds. Thus, the dish can move from 15 degrees to 110 degrees elevation. The total weight of the moving parts of each of the 30 45-meter diameter antennas is about 85 tons. This excludes the counterweight, which itself weighs 33 tons. Radio waves reflected by the wire mesh surface are picked up by the antenna feeds at the focus. The feeds are mounted on 4 faces of a rotating turret box. The antenna feeds are dual polarized. The front end electronics is also mounted on the turret box. The assembly shows various feeds and the connected front end electronics. The received signals and control signals travel on about 25 cables. These cables come up through an azimuthal shaft where they are anchored on steel rings supported by steel chains. This simple cable wrap system ensures minimum twisting of the cables as the dish rotates through 270 degrees in azimuth in either direction. The concrete tower shell houses the electronics for rotating the dish. It also houses the electronics which connect the front end at the focus of each dish to the central electronics building. About 60 kilometers of mono-mode analog optical fiber link is used for conveying signals received at each antenna to the central electronics building. The signals received from the antennas are processed using sophisticated electronics. The low-noise front-end amplifiers, the local oscillator system, the baseband electronics are extremely complicated. The correlator system is made by using ASIC chips specially designed for this application. It can produce a 256 spectral line channel of complex visibilities for each of the 4 polarization products for 435 interferometric baselines as often as once in 4 milliseconds. The offline processing of these observations can keep the most powerful computers busy for hours for each set of observations. When the source is observed for about 10 hours, an image can be reconstructed as if the source were observed with a single giant dish 25 kilometers in diameter. The observational technique is called Earth rotation aperture synthesis. In the coming decade, the GMRT will be rewarded with many important discoveries and insights of the universe. Equipped with this powerful instrument, Indian radio astronomers are waiting for the universe to reveal more of its mysteries and wonders.